Okay, so let's start. So last time we talked about the limit of two variable function, or a special type of multivariable function, and also about the continuity of two variable function, and we gave an example of proof of continuity of two variable function and the counterexample of discontinuity or non-existence of limit of two variable function. So what you are seeing in this slide is the proof of the non-example of discontinuity of a two variable function. So let me summarize. You can check check your continuity or discontinuity by first epsilon delta method. This is for proving continuity or finding a special path when you prove discontinuity, or you can check, this is not rigorous, but you can check your continuity and discontinuity by drawing the graph. You should find any hole or cliff for discontinuity. So from now on, we are going to talk about the differential. So before we start, let's review what was the differential or differentiation of a single variable function. So in single variable function, the easiest way to describe a differential is it's the slope of a graph. So when you have a graph like this, y equals to f of x, and say you want to find a differential at x0 on x-axis, then it gives the slope of tangent line is the graph it's the differential of the function, slope of the tangent line at x0. So, and if you want to generalize this kind of concept to two variable function, there are several problems. One of the problem is that we don't have a tangent line on the graph of two variable function, because the graph of two variable function is generally a surface, and the surface has tangent plane, not tangent line, right? Or if you want to specify a tangent line, there are infinitely many tangent lines lying on this tangent plane, so you cannot specify one tangent line. And there are other problems. If you don't have a function like z equals f of xy, then the graph of multivariable function is somewhat weird thing, not just the surface. It could be a parametric curve or other things, or like three-dimensional thing in four-dimensional space, something like that. So this kind of geometric description of differential doesn't work for multivariable function, and we don't even know what to call as the differential of a function, because in one variable function we call this f prime, defined as a real number, and it represents the slope of a tangent line. But what about the differential of two variable function? Is it a number or not a number? So before we give the most general definition of differential, let's think about the easiest way to generalize the differentiability or differential of single variable function to two variable function. So what we're going to do is give a direction from a given point in two-dimensional plane. So say I pick the x0, y0, and I give a direction u, a comma b as a unit vector. Okay, so it's a length 1 vector, and I want to define a limit of this ratio. So numerator is the subtraction of a value of function at x0 plus at and y0 plus bt, and then with a subtraction with f of x0, y0. Okay, and then we divide by t. So if this limit exists, then we call it as u directional derivative at x0, y0 and denoted by duf. So it might be weird by first sight. So let me give a geometric meaning of what this u directional derivative is. So here is our picture of a surface, a graph, and here is our domain, or just xy plane, and here's our z plane, z axis. And let's say I have point x0, y0 here, and this is the point on the surface whose first two coordinates are x0, y0. And let's assume that my u direction is this way. This is my u direction. What I'm going to do is put an extended line along this u direction, okay, along this u direction, and then put a plane, vertical plane on xy plane, parallel to this line. So I put line here like this, and then this kind of plane intersects the surface of a graph, right? So let me give a section or intersection of the plane and the surface of the graph. Okay. So this blue one is the intersection of surface, the graph of surface, and this plane P. So P, the plane orthogonal to xy plane and parallel to u direction. Okay, they are unique plane having this property. So now you have a section of a surface, and I want to look at this section as a curve inside of two-dimensional space. Which two-dimensional space? It's the P plane. Okay, so let me take this P plane here. I don't want to put axis here, but just put a line, horizontal and vertical line, as if it's a xy plane, but this is actually a P plane. And there is, so okay, so the vertical line, vertical axis, actually a z axis, but this is parallel to u direction, and there is a section, it's the same section, the intersection, and in somewhere there is, here we have x0, y0. So what we are looking at is the slope of a tangent line at this point on this section, which is, that's the u directional derivative. The slope of tangent line at x0, y0. So let me rewrite this. Tangent line at is duf x0, y0. Okay. So let me think again. So what we are looking at here is the ratio. So this whole thing is the ratio between the difference of value of f, diff of f and difference between the direction of u, difference of parameter t. So when parameter t changes from 0 to slightly bigger or smaller than value than 0, then you have move along this curve, move along this line in xy plane, starting at x0, y0, that's when t equals to 0, to the direction of u or minus direction of u. So I want to check how the value of function changes by moving my points along this parameterization curve, parameterization line right here. Okay. So in other words, I can put this u-directional derivative in different words. Let's say I put ct as x0, y0 plus tu direction vector. Then this u duf at x0, y0 is the limit of t goes to 0, t over, so t the denominator, so fct minus fct0, right? So the first part, x0 plus at comma y0 plus bt, is nothing but a point on this parameterization curve ct at the time t, and the second part is c0. Okay, so I'm looking at the difference between these two values and divide by t. So what I really do is the following. I'm taking the difference of value of composition of two functions, f and c, and by definition f composite c is a single variable function, right? So I can this definition of limit is nothing but taking a differential of the single variable function f composite c at t goes to 0. So this is d dt when t goes to 0 of cfc. So in other words, this is nothing but f composite c prime 0. Okay. So you should remember there is another way of describing your directional vector, directional derivative in single variable function. So if you have any question, please stop anytime, or I give you an example. So let's say we have f of xy equals to x squared plus y squared, and we want to find one zero directional derivative of f at this special point. So 1, 0 direction is the unit vector, obviously, and it's actually pointing to the x direction. So in two-dimensional plane, here is my 1 over 2, 0, and my direction is this direction. Okay. This is my u, 1, 0. So you can use the definition of the directional derivative and just plug in the formula here and to get this one, or you can use the above reformulation of the directional derivative. So you can also use this directional derivative of single variable function. So the question is duf a scalar or vector? It's a vector. The reason why it's a scalar in this example. Okay, in general it's actually a vector, but because we have a function, since f, the value of f, value of f is scalar because we put z as a real number. The directional derivative is scalar. Okay, if the value of f is a vector, then duf is a vector. So it depends on the type of the value of your function, the type of the directional derivative of your function. But we are talking about the real valued function f. So the directional derivative is a scalar. So here you also get the scalar 1. So if you want to use the second definition, let's try to compose these two functions. So Ct is nothing but a parameterization line written by this way. So in other words, Ct is 1 over 2 t comma 0. So if I composite f and c, I get 1 over 2 plus t square plus 0 square. So therefore, we have 1 over 4 plus t square, right? And then the directional derivative is simply a derivative of this single variable function at t equals to 0. So what we have is we get rid of this 1 over 4 and 2t disappeared because t equals 0, so only 1 remains. So we have same value. All right. So let me read out this remark. For single variable function y equals to f of x, the differential represents the rate of change of f of x as x approaches to, there's a typo, x0. The directional derivative extends these concepts. Okay, so when we have a line ct equals to x0 y0 plus tu, then when ct approaches to x0 y when t approaches to 0, ct approaches to x0 y0. So if you take a composition of f and c, then it becomes a single variable function, and we have this ratio. Okay, that's what we already showed in the previous slide. And what directional derivative says is that it's the rate of change of value of function along the straight line passing through that point x0 y0 parallel to u, which is u1 u2. Okay, so in other words, you can put a plane parallel to both this direction u0 u1 u2 0, the three-dimensional vector, and this k directional vector, which is parallel to the z-axis, and which contains this point, and then you take the section, and the slope of the section at the x0 y0 becomes the directional derivative. All right, so once you have a notion of directional derivative, and suppose that you can take the directional derivative of a given direction vector at any point, then you can define a new two variable function out of the directional derivative. For example, let's say we have a function f, and we define a u direction, a fixed direction, and we assume that this duf always exists for any xy in the region of domain. Then we can define a new two variable function called gxy. This is the random name I just gave, and let's suppose that this g has a value of directional derivative of f to the direction u at xy. Okay, so we have given with this new two variable function, so why not we can take another directional derivative of this new multivariable function. So let's do that. So what we do is we take the second directional derivative of f, which is defined by the directional derivative of this new obtained value, a new obtained function g. So in principle, what we are actually doing is we first take the directional derivative of f to the direction u, and also again we take the directional derivative in terms of v. Okay, so this is called the second directional derivative, and the reason why it's important is because we're going to specialize our directional derivative to partial derivative, and this second order directional derivative enabled us to define the second order partial derivatives. So let's try to give an example here. So here's an example of two variable function like this one, and let's first find duf. So I didn't specify a point to find a directional derivative. That means I want to find a two variable function whose value is defined as the directional derivative. This is two variable function, not a value. Okay. So first of all, follow the definition. Duf xy is equals to, let's say t goes to 0 of f x plus u direction 3/5t y plus 4/5t minus fxy divided by t, right? So the long computation. Okay, so we have t goes to 0, so 1/t taken out. So we have instead of x, we have x plus 3/5t, x plus 3/5t cube 5 x plus 3/5 t square, and y plus 4/5t, and then y plus 4/5t cube, and take x cube minus 5x squared y minus y cube. Okay, so when you have this kind of example as a problem, don't try to do this by your hand. You can, but if you want to try to type this entire equations, it's very tedious work. So I will tell you how to do this in MATLAB, how to do this long computation symbolically in MATLAB after the lecture. So try to do this in MATLAB. I'm doing it by hand for your information. So first of all, let's take out this x squared terms. Here we have 1/t, and x squared here in here cancels out, and what left is 3 times x cube I square 3/5t, and then blah blah blah, because the rest of the term from x plus 3/5t square I cube contains t square instead of t. But if you have a t square, then because we are going to divide the t out on everywhere, t still remains if you have a t square. So when t goes to 0, it all disappears. So I'm not going to write the rest of the parts. So how about the second part? We have 5 xy. Here is 5x squared, and y cancels out. And what left is we have, I have to actually write everything here. Let me erase this. X squared plus 2 times x 3/5t plus 3/5t squared, and y plus 4/5t, and take this x squared 5x squared y, and then let's finish the last one first. So we have plus 3 times y squared 4/5t, and blah 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 here. So let's look at this part. If you have these ones, if you have these parts, it has t squared, it contains t squared, so I said it will disappear. So what remains is when you have only 1t. So the only way you can get a 1t is that you can multiply this part and this part. If you multiply this this part and this part, you get still 2 t's. So what I get is 1/t and 3x squared 3/5t plus 5 times 2 times x 3 over 5 t times y. So this part is cancelled out already. This part. So this one and this part cancelled out. And also the 3 times y squared 4 over 5t. Okay. And so I'm taking limit, so I can do this, even though the actual formulation is different, but I'm taking a limit, so the value of the limit is same. So take out this t, so get rid of t everywhere, so we have t, 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 and t. So we get 9 over 5 x squared plus 6xy plus 12 over 5y squared. So that's the two variable function duf. Okay. So what if you take another duf? That's another long work, but you have to do this on this function. Okay. These functions. And it actually becomes really tedious, so I'm not going to do this. There's an easy way to do this once you know what the chain rule is, but for now it's just an exercise, so you can do this similar method on this new function duf again. So I'm not going to do this again. Okay. Now we are ready to talk about the directional derivative and a partial derivative out of directional derivatives. So directional derivative can take any unit vector as the direction, but when you're talking about the partial derivative, you only take the unit vectors, unit basis vectors. So when you're talking about two variable functions, your domain is on two-dimensional plane, so there are two unit basis vector. One is E1 and the other is E2. So if you take the E1 directional derivative, it's called the x partial derivative, and if you take the E2 directional derivative, it's called y directional derivative, y partial derivative. So they have a special name, dx and dy, in each direction, EU, E1 and E2. So dxf and dyf are called the partial derivative of two variable function, and if you specify the point that you're taking derivative, then it's called the partial derivative at that point. So there are other names for the partial derivative, other symbols to denote the partial derivative. One is dxf or dyf. Other is you can just put x and y on the subscript of function f, or you can take the curly d instead of the d, Roman d, to indicate that it's a partial derivative, not the normal derivative. So if you see in any formula, in any context, in any subject of study, this kind of notation or this kind of notation, there is a big difference between these two. So if you see this df dx, it assumes, it means f is a single variable function on the variable x. So f contains only x as independent variable. But if you see this notation, the curly d, then it says f has x as an independent variable, but f has more. Okay, because we don't know how many or what other variables are, but at least this curly d partial derivative notation means that f is not the independent variable of f is not consist of only x. There are others. Okay. Also, so you can define a second order partial derivative similar to the second order u-directional derivatives. So in this way, so the usual notation to describe the second order partial derivative is that you put the squares on above of the curly D notation, similar to the second derivative of the single variable function, or you can put this subscript twice, or you can use this kind of notation. But the order of your notation is important. So suppose that I'm taking partial derivative of y and then take the partial derivative of x. Okay, so then you have to rewrite this as yx, and in this notation it's opposite because usually it's yx again. So usually when we put the subscript as indicate the partial derivative, we kind of mean that this is taking a partial derivative of y first and then x. So the order of x, y are reversed here, and in the first notation and second notation here. So you have to be careful. So the easy way to remember how the rule of the order of this notation is that so think about this curly D notation. What you're doing is df dy and then take another d dx. Okay, so that's why we have dx and then dy. So here the reason why y comes first is that you're taking partial derivative in this parenthesis order. Okay, the same thing for others. So if you take the same variable twice as a partial derivative, it doesn't matter the order. So why the order matters? Because in general, if you take the fxy and fyx, it's different function. You get the different value. Usually it has the same value. It gives the same function. But there are examples of function that this value of second order derivative is not the same. Here's an example. Let's try to get the partial derivative of these two functions. Did I put that as a remark? So let me give a remark. So if the partial derivative is defined at x0, y0. So if you assume that we know that a partial derivative at that point exists, then this f of x can be easily obtained by taking the derivative of x as if y is constant. So when you take a partial derivative on x, think about y as just constant, meaning that you take a derivative of x of y itself, then it disappears because it's a constant. So do this for every other component of your function, then you get the partial derivative. So for example, if you have this kind of function, then the function has this formula as long as x and y are not both 0. So f of x, so let me put it here, f of x, xy is the partial derivative of this big function x squared, y squared, and xy, x squared, y squared, when xy is not equals to 0. Why? Because when you do this computation in the remark, what remark said, then what we get is the derivative of fraction of functions, one as if it's a one variable function, because I took y as a constant. So here we have x squared y square as a denominator, and in the above numerator we have y x squared y square plus xy 2x. You see, I already omitted y square here, because if I take the derivative on x of y squared, because it's a constant, it's considered as a constant, so it becomes 0. So we get this one as the derivative of the numerator times x squared plus y squared. I need more space. And minus of xy, x squared minus y squared, times the derivative of denominator becomes 2x. Okay. Okay. Let me do this in hand. Should I? Let me tell you right now how to do this in MATLAB. So remember that formula. So here, so I'm going to define a symbolic variable x and y. And let me rewrite the formula here. So let me define y x squared minus y squared plus x times y and 2 times x times x squared plus y squared minus x times y times x squared minus y squared and 2 times x. So this is the numerator. I put big parentheses about an entire formula, and then divide by x squared plus y squared. So this is a symbolic expression, so I don't need to put a dot above every hat here. So what I want to do is first look at the formula to see whether I put the formula correct. Okay. And then I want to simplify this. Simplify the entire formula. So the result is this. Okay. So I want to just copy that formula. So copy it. Okay. So that's y times x fourth 4x squared y squared minus y fourth divided by x squared y squared square. Okay, so that's the value of function of the partial derivative of fx when xy is not equals to 0. But what if here, what if xy equals to 0? So if you try to plug in x and y equals to 0 in this formula, in this formula, you get 0 in denominator. Numerator also goes to 0, but because denominator is 0, the value is not defined. Okay, and if you try to get the limit, it fails also. So what I need to do to find the value at x0 at 0,0 is just follow the definition of the directional derivative. So there's a typo, I don't need f here. So fx 0 is by definition it's directional derivative of f in the direction of 1 0, and this is equals to t goes to 0 of t over 1 over t times. So my parametric line is t, 0, So I'm putting f of t comma 0 minus f 0 comma 0. So what I get is 1 over t times, so when I put y equals to 0 here, then everything actually becomes 0, no matter what what the value of others are. So I always get 0, and I already defined my function f to be 0 when xy is equal to 0, so that's also 0. So we have 0 over t, so that's always 0. So we get 0. So this is 0. Okay. Alright, so let's try to find out what fxy is. Okay. Do I have? Okay, so let me give a another page. So fxy at 0, 0, which is, I'm taking fx as a two-variable function and then take a partial derivative on y variable at 0, 0. So first of all, I could find fy xy when xy is not equals to 0 by taking a partial derivative of this long formula, by taking x as a constant and y as a single variable. But we really don't need that, because I just want to find the partial derivative at 0, 0, so I can just find the partial derivative of in the direction u-directional derivative of in the direction of 0, 1 of fx at 0, 0. Now, by definition, we have t goes to 0, 1 over t, and I'm plugging 0, t as my parametric curve, parametric line. So I'm going to plug in fx 0t and then subtract by fx 0. So we know that this fx 0 is 0 because of this result. And if I plug in x equals 0 and y in t, what I get is, so everything becomes a little bit simpler. So I have t fourth and t times minus t fourth. Okay. So I have canceling between t and t fourth and t fourth. So we have minus 1. So value of second order derivative in x and y order at 0, 0 is minus 1. So what if we take fyx? So in order to do that, we actually need to find the value of the formula of fy instead of fx. So let me do that. So let me also show you how to do this in MATLAB. It's very easy if you know the symbolic math toolbox. So let me go back to our code. So we have, so since I already defined my symbolic variable, I don't need to put this extra command, but I'm doing this for safety. And I defined my f to be, what was the f? X times y times x squared minus y squared divided by x squared plus y squared. Okay, and I don't want, okay, so first of all I define f to be this formula, and let's try to take a derivative in terms of y. Diff of f of y, it's a comma here. Okay, so this is a different partial derivative of this function f in terms of y. So it's very long. I want to simplify it. So put the simplify around here. So we have this simple formula. Okay, so let's copy it. So fy is minus x minus x fourth plus 4x squared y squared plus y fourth divided by x squared y squared. So if you want to define find fyx 0, 0, what you're actually doing is fyx 0, 0, therefore it's d10 of fy of 0, 0. So this is by definition 1 over t times, so I'm taking fy as my function, so t0 minus fy 0, 0. So when I plug in x as t and y as 0, this formula becomes t, is there a square? Yeah, there's a square here. T fourth and minus t times minus t fourth, and all the y parts becomes disappear. So and minus 0. Did I compute dy? Oh, I didn't actually compute the fy 0, 0. So sorry. So I need more computation, more calculation for this part. So fy 0, 0 is nothing but 0, 1 directional derivative of f at 0, 0. So this is limit of t goes to 0, 1 over t times f of 0t minus f of 0, 0. So this is, so what is f0t? So when x is 0, if you look at the formula, here is x, so everything goes to 0. So this is 0, and f0 is defined as 0, so this is all 0. So because of this result, we know that this is also 0. So then there's a cancellation. So we have t cancels out, t4 cancels out, and we have a minus, 2 minuses. So the result is plus 1. So compare two results. We have fyx at 0, 0 as plus 1, and fxy 0, 0 at fxy 0, 0 as minus 1. So this is an example that fxy and fyx is not always equal, right? So order of partial derivative matters. So you cannot interchange the order of partial derivative. Yeah, so, but let me give another remark. So if you take these two partial derivatives are all continuous at x0, y0, then these two values are actually same. So what does that mean? So our previous example, this example, has a partial derivative fxy and fyx not continuous at 0, 0. So that's why we have different value. Okay. But if you have a continuous second order partial derivative, then you can actually have a same value, so you can interchange the order of partial derivative. So this is some theorem from analysis, mathematical analysis. So you're not going to prove this, but just remember this. But also be quite careful that it doesn't work for every functions. If it doesn't, this condition doesn't hold, then you don't have the same second order partial derivatives. Okay. If it's too fast, then please let me know. I can revisit previous slides and give more detail. or I can just keep moving. So now we know about the partial derivatives. So basically, partial derivative is the directional derivative, and the directional derivative is slight generalization of the first order derivative of single variable function. Now we are ready to talk about the differentiability of two variable function itself. So the concepts are different. We want to talk about the differentiability of a two variable function. It's different from saying about the partial derivative or directional derivative of function. First of all, I'm going to assume that there is a partial derivative of f at x0, y0 to the direction of x and y. And then I'm going to define a new function, L, also two variable function, defined in this way. So we have a scalar, fixed scalar, three fixed scalar of f and fx and fy at the same point x0, y0. And we multiply x minus x0 and y minus y0 to fx and fy. So this is a linear function because only variable, independent variable appears in this formula is x and y, and order, the degree of this x and y are 1. So degree 1 polynomial, degree 1 polynomial. So this is called the linear approximation of function at x0, y0. Okay. So the remark is that if you take the graph of this function L, z equals to L, then this is the tangent plane to the graph of our original function f. So this is actually important later on, so I'm going to give you a picture of what it says. So here is your graph of function, the surface. So it's some curved surface, and here's our z, and here's our y, here's an x. So let's say we have point x0, y0 here, and here is the point above the surface. And the remark says that I can put a tangent plane at this point, which is tangent to that point on the surface, and it is the graph of the linear approximation y. So think about the tangent vector on the surface, the graph of function. So how do we get the tangent vector? I want to get actually two tangent vector of the surface at the point. So this is our point of interest, P. Want to get two tangent vectors at P on the surface of graph of function. How? First, you take two direction on xy plane. So let's say this is my E1, actually that's E2 direction. So it's E2 direction, and take E1 direction. Okay. Take E1 and E2 from our point x0 and y0. And let's look at the trajectory on the surface whose projection is the parametrization line passing through x0 and y0 to the direction of E1 and E2. So I'm going to set this CT to be x0, y0, 0. Does it make sense? No, actually. Let me just put it this way. So x0, y0 plus t times, let's say C1, okay, E1, so which is x0 plus t, y0. And C2 as similar, so it's x0, y0 plus t. So consider two parametric curves. One is D1, which is composition of C1 and F, and not composition, sorry, consists of x0 plus t y0 f of C1 t here, and D2 given by x0 y0 plus t comma f composite C2 t. Okay. Then I'm going to take a derivative of d1 and d2 at t equals to 0. So if you have a parametric curve in three-dimensional space, if you take the derivative of that parametric curve, it gets the direction vector or velocity vector at that parameter t, right? So d1 prime 0 is, so, and also when you take a derivative of parametric curve, you take the derivative of each coordinate functions. So consider each coordinate as a function of t. The first one becomes simply 1, and second one is just constant. So when I take a derivative in terms of t, it becomes 0. How about the third one? So it's the ddt at t equals to 0 of c composite c1 f composite c1 of t. So we defined this to be directional derivative of the function f in direction of c1, which is e1, right? e1 f at x0 and y0. But that's nothing but the partial derivative of f. So this is 1, 0, fx, x0, y0, right? Now how about d2 prime? If you do this, then it becomes 0, 1 again. So t is on the second coordinate. And if you take the derivative of the third coordinate, it's f of y, x0, y0, right? So what does this d1 prime, d2 prime indicates in our previous picture? So here's curve, parametric curve on the surface along this E2 and E1. Okay, so this is D2 and D1. So C1, C2 are here. This is C1 and this is C2. And the tangent vector to direction of D to D1, this is D1 prime 0, and here is D2 prime 0. So D1 prime 0, D2 prime 0 are tangent vector to the parametric curve of D1 and D2. And D1, D2 are lying in the surface of graph of functions, so D1 prime and D2 prime are tangent vector of the surface at the point P. So that's the important part. So these two, these ones are tangent vectors at x0 on the surface, which is the graph of function. Okay. Now what we have to do is try to find a normal vector, orthogonal vector to the tangent plane. How do we get that tangent orthogonal vector? You can take the cross product. So take the cross product of d1 prime, oh, I shouldn't put this, d1 prime and d2 prime. So by definition, we have d1 prime equals to 1, 0, fx, and d2 prime as 0, 1, fy. I omitted x0 and y0 for simplicity, but there should be one because this is not a function, this should be a scalar number. F1, fx and fy are scalar. So y part, we have minus fx, I and j becomes minus fyj, and k is just k. So what we get is minus fx x0 y0 minus fy x0 y0 So this is our normal vector. So once you know the normal vector of the plane, now you can define your tangent plane. So this is xy, it's a set of points x, y, z, where minus, if you take the inner product with this normal vectors of x0, y minus y0, and z, there's a space here, so z minus fx0, y0, then it must be 0. So let's rewrite this formula. We have minus fx x0, y0, x minus x0, fy x0, y0, y minus y0, and z minus f x0, y0. That's the formula of inner product, and that must be equals to 0. That's the equation defining the points on this plane. So let's move along, move everything except for this z to the right hand side of the equation. So z is equals to f of x0, y0, and plus fx x0, y0, x minus x0, and fy x0, y0, y minus y0. So you see the right hand side is exactly same as formula of lxy. So this is lxy. So therefore z of lx, this graph of L is the tangent plane at x0, y0, f x0, y0 on this surface. Okay. So why we are talking about this linear approximation as a tangent plane? So as I said, if you want to generalize the geometric concept of differential of single variable function, meaning that it's a slope of a graph, then in the two-dimensional version or three-dimensional version in the surface, you need to generalize that tangent line to tangent plane. Okay, so that's why we're talking about the tangent plane. However, the definition of differentiability is a little bit different from the single variable function. So if you be patient, I will explain why this definition extends the definition of differential of single variable function, but let's take as a fact here. So this is a definition. So let's assume that our linear approximation is given by Lxy. So it assumes that fx xy and fy x0 y0 exist. Okay, so having a linear approximation a priori assumes that there is a partial derivative at x0 y0, and we say a function is differentiable at that point if the following holds: if the limit of this ratio becomes 0. So what does that mean? So let's split the component here. So on the denominator we have a difference between the value of function and the value of linear approximation, and on I'm actually numerator, and the denominator is nothing but the distance between the point xy and x0 y0. Right? So if you consider xy as a vector and x0 y0 also a vector, then it's a norm of vector subtracting these two. So what does that mean? So it says that the difference between xy and lxy gets smaller to 0, but in the speed faster than x approaches to x0, y0. So there is a distance between x and xy and x0, y0, and the distance becomes closer to 0. But the difference between the corresponding value of functions on f and l are getting smaller even faster, so that the ratio actually becomes 0. So numerator and denominator both goes to 0. So if you have a 0 over 0 of a limit, then you have to compare the speed of how fast that approaches to 0. Since we assume that this limit is 0, the speed of approaching to 0 on the numerator side is faster than the speed of approaching to 0 on the denominator side. Okay. Okay, so here's maybe I should explain at this point why we have this kind of differentiability of two variable function, and how is it different from the differentiability of single variable function. So here's a remark. So let me give another, restate the definition of differentiability of the single variable function. In single variable function y equals to f of x, we say fx is differentiable at x0 if x goes to 0 over x0. fx minus fx0 exists, right? So if it exists, the value of the limit is called the differential, and we denote it by f prime x0. But we are only talking about the existence of differential, or differentiability, in other words, of the function. So this is the definition of differentiability of single variable function. So let's say we call this limit as, let's say let's say c, okay, for example. Then we can rewrite this equation as follows. So put everything on the right hand side. So we get x goes to x0, x minus x0, and fx minus fx0, and then there's a minus c, but I want to put that in the numerator side, so we have c times x minus x0. Okay, and then let's put the parentheses. So fx minus of fx0 plus cx minus x0. So what does it look like? So we have in this big parenthesis, this is the function of slope, tangent line, sorry. Right? So what we are actually comparing when you're talking about this, the differentiability of a single variable function, is the difference between the value of function and the value of the tangent line. Okay, and take the ratio between the difference of value and the difference between the value of the variable x. So if the ratio goes to 0 as x approaches to x0, we say that single variable function is differentiable. And what happens in this the formula, the c serves as the slope, and we define that as a differential of the function. So our definition of differentiability of two variable function is just a generalization. So same as the single variable function, we have minus Lx over x minus x0. So instead of we take the single variable function, we take the two variable function. So in other words, I can also put the parenthesis here, the absolute value sign here, so everywhere here, because if the ratio approaches to 0, it doesn't matter whether it approaches from the negative or positive. So I can just look at the positive side, or I can just put the absolute value sign around the entire ratio and then see whether it goes to 0. So I can put the absolute value sign, and that actually becomes a special case of the definition of two variable case. So that's our definition of differentiability of two variable function is a generalization of differentiability of single variable function. Okay, so we're not talking about different things, we're only talking about the same thing in slightly general version. Okay, so I found this very interesting. Actually, I first learned this fact that I can generalize our differential concepts of single variable function to multivariable function. I hope you can also find it interesting, and it gets actually more interesting when you're talking about more general types of multivariable function. We are only talking about very special type of function, which is z equals to f of xy type of multivariable function, but there are infinitely many types of functions, right? So you can generalize the differentiability of two variable function even further to define differentiability of general multivariable function. Alright, so that's example. Let's look at them. The existence of linear approximation does not imply that f of y is differentiable. Find an example of function which has linear approximation at 0, 0 but not differentiable at 0, 0. So one example is that, let's say, so before I actually give an example, let me restate what it says. So you may have a linear approximation, but it doesn't imply that f of xy is automatically differentiable. So you might have a function which is not differentiable, but it has a linear approximation. So what are they? So here's an example. Before I give this example right away, let's think about the single variable case first. So let me define a function x times sine 1 over x. Okay, or let's say x squared, sorry. I think it's better. So when x equals 0, it's 0. When x is not 0, then it's x squared times sine 1 over x. So the graph looks like the following. So this is an asymptotic curve, so it's a sinusoidal, but the wiggling gets very dense when x goes to 0, right? So this is y. Now think about the tangent line. So if I define my L of xy, or I should take first f prime 0, the definition says when t goes to 0, I need to take ft minus f0. So it says that ft is t sine 1 over t, and f0 is 0, so it's 0. And we have cancelling out tt. And sine 1 over t is always bounded by minus 1 and 1. So when you multiply by t, it always goes to 0. So we have a slope. I don't know what slope, I don't know which slope that is, but I know actually the differential of the function actually becomes 0. So I know that L of x is x0 plus 0 times x minus 0, which is 0. So I can define a linear approximation of this curve as simply a 0 line. The y goes to 0. But then, if I simply rewrite this definition of differentiability of single variable function, what happens is that when t goes to 0, the difference between ft and lt doesn't exist. Oh, does it exist? So t. Wait, I want sorry, so I want a non-example here. So so t here, ft. So if I do this, then I get t squared sine 1 over x, sine 1 over t minus 0 over t. So wait, something is weird. So I want non-example. If I have t squared square root of t. Oh, okay. Yeah, I was confusing about the continuity and the differentiability here. So okay, so maybe this is not a good example, because now if you want to define a linear approximation of single variable function, I should already know what the differential of the function is. Then it already assumes that there is a differential. It already assumes the differentiability of the single variable function. So right, it's not a good example if I do this in the single variable case. Right, well, let's just conclude this. So anyway, if I do this, then I get t squared cancels out. We have t here still remaining, so it becomes 0. So it's differentiable obviously. So I already done this when I compute f prime 0. Let's try to do similar in the case of fxy equals to x square y square sine 1 over x square y square here. Okay. So first of all, I want to find a linear approximation. So let's try to get fx 0, 0 and fy 0, 0. And a separate page here. Then fx 0, 0 by definition it's 1, 0, f of 0, 0, right? So this is nothing but the derivative of t equals to 0 when I plug in t, 0 in the function f. So when I do this, this is nothing but, oh sorry, so I should define when x equals to 0, 0, so it's defined as 0. Okay, so that's my function, two variable function. Oh, okay, so I forgot, I missed your question. So let me go back to the question again. So why we put the absolute value sign on the definition of the differentiability of single variable function? Because when you want to assert that the limit goes to 0, it doesn't matter whether it goes from the negative side or positive side. So both goes to 0, then we can only check the absolute value of the sign, absolute value of the value, and take the limit so that it goes to 0. So in other words, when x, or say when some function, let's say a row of x goes to 0, then it's the same thing as saying that the absolute value of row goes to 0, or x doesn't have to go to 0, so x is 0. Okay. Okay. So let's compute these two value here. We have it's a ddt of t equals to 0 of t squared sine 1 over t. Actually, it's not actually we need an entire formula, t squared sine 1 over t 0. So when t equals not 0, when t equals to 0. So same thing for above what we did. So this is equals to 0. Okay, and same thing for when I take the partial derivative in terms of y, it's also 0. And we know that the value is 0, 0 is 0, so we have linear approximation which is 0. T So I'm sorry, so I should think about this more carefully. So this is actually differentiable. So think about the definition again. By definition, what we have to check is when x, y approach to 0, 0, x minus 0 square plus y minus 0 square divided by square root of fxy and yxy to be 0. So think about xy goes to 0, 0. Now this is x squared y squared, and fxy is this guy, because we're not getting to the x0, we're not actually at 0, 0, so we follow this formula here. Okay, so we have x squared y squared sine 1 over square root x squared y squared and minus the L, which is 0. So we have limit of xy goes to 0, 0 of square root x squared y squared sine 1 over x squared y squared. Well, actually that's 0. So we merely show that this function is differentiable. I want the function which is not differentiable, right? But still have the linear approximation. So what's wrong here? So okay. So I think the problem is that right, when I define my linear approximation, I already assumed that fx and fy, the partial derivative, exists. But the problem is that there is another way to define the linear approximation. So okay, I don't think it's a good idea to give another name, another definition of linear approximation that makes you confused. So I think it's easier to change the example here, or just get rid of just skip it. Okay, just skip this. I think it makes you more confusing. So just use this example as an example of differentiability of functions. Okay, so if you have given by this kind of functions, then you can get a linear approximation, and also the definition of the differentiability shows that it's also differentiable. Okay. All right, so I think it's better. So okay, so look at this example and this one. And after we've done this, maybe we should finish our lecture here. So let's show that this function is not differentiable at 0, 0. Okay, so we first need to find the linear approximation and then tries to show why it's not differentiable. Okay. All right, so let's try to compute the linear approximation first. What is f of x 0, 0? Are we talking about 0, 0? Yes. Okay, that's why. So by definition, we are talking about when t goes to 0, 1 over t of ft0 minus f0, 0. So when I plug in y equals to 0, then you see there is a y right here. So everything goes to 0. So this is limit of 0, so it's 0. How about fy 0, 0? So that's also 0. I'm sorry, so it's similar, not same. 0t minus f0, 0, and it's also 0. So Lxy is 0 plus 0 times x minus 0 plus 0 times y minus 0. So 0 function, the just xy plane itself, is a linear approximation. And let's plug that into the definition of differentiability. So we have xy approaches to 0, 0, and we have x squared y squared square root as a denominator, and we want to compare the difference between fxy and lxy, but lxy is 0, so everything disappears. So we have xy goes to 0, 0, and if you look at the formula again, this is our formula. So we have x squared y squared and xy above. So we need to ask whether this limit is 0. Now we are back to the business of calculating the limit of two variable function. You can draw your graph of function and then see if it can have a limit. If it doesn't show you clearly that it has a limit at 0, then you have to actually compute the limit using epsilon delta method, by when you prove the limit is something, or if you want to prove that the limit doesn't exist, then you have to give counterexamples. Actually, you need a hunch. You need first guess whether this limit exists or not. Because I already saw this kind of problem many times, I know that this cannot have a limit. Because usually if you have a same degree of polynomials on denominator and numerators, then the limit doesn't exist. So let me give an idea of my hunch that the degree of numerator and denominator are same, equals to 2, and usually the limit of such ratio does not exist. Okay, so if you guessed that the limit doesn't exist, then you have to find at least two paths which converge to different values. Okay, so try your value path C1t as t comma t and C2t as t comma 2t. Okay, so when I plug in C1t, then the limit becomes t goes to 0 of 2t squared t squared, which is 1 over 2. So already it's not 0, so we are already done, right? But let's try one more thing. We have 5t squared and 2t squared, so it becomes 2 over 5. It's not also 0, but it's also different from the previous limit we found. So the limit doesn't exist. It's not the limit exists, but it's not 0, but the limit already not exists. So we know that this function is not differentiable. 0, 0. So by the way, actually, so I take back what I said. This example actually shows this example of the previous example, right? So this function has a linear approximation, but it's not differentiable, right? So I was thinking about other examples, but I failed in the previous example. But the second example actually gives a solution to the first example. Alright, so this is what I already explained, and so here's another theorem. I want to try to give you the what is remaining in our slides. So once we have the definition of differentiability of the special type of multivariable function, then we need to generalize to multivariable function of the general types. So then we need a notion of gradient and notion of differential as a matrix, and then we can define more general the differentiability of multivariable function. So I will explain these two slides in the next time, but let me do some questions here, problems, right? Okay, so problem 1, draw the graph of these two functions. So I think it's not hard, actually. We've done some of the graphing in the previous lecture. So let me do the first one. So let's see, I want to define a function x in two variable, x times x squared minus y squared, and xy is mesh grid in space -1 to 1, and I want to graph surf y fxy. Okay, here. Something's weird. X, Y, X, Y. In space -1 to 1 mesh grid. I'll draw it again. This is not the correct answer, so x times okay, x times, okay, so I forgot to put dot here. Okay, so this is the graph of our first problem. You see, it's not a saddle, but it's called also saddle. So there's a name for this saddle. That's monkey saddle, because usually your saddle on a horse needs your two legs to fall down, but monkey has a tail, so and two legs, so there is a 3 ways of falling down here. So monkey can put 2 legs left and right here, and then tails to here. Okay, so that's called the monkey saddle. That's why you call the monkey saddle. All right. So you can do the second problem yourself, and let's look at this one. So show that y the limit doesn't exist. So if you want to prove that the limit doesn't exist, you can find special paths, at least 2 paths, such that your function doesn't converge to the same values. So for example, in this case, it's actually same thing as we done in the previous example in here. So it's almost same, right? So try ct equals to t comma t and C2t equals to t comma 2t, and C, so if you put this as fxy, and C, this fc1 and fc2 converge to different values. Okay, so question, right, so existence of tangent plane does not guarantee the differentiability of multivariable function. You're right, and I'm not saying that it's an accurate definition of differentiability. I'm saying that the most general definition of differentiability exists, and we're going to do that in the next lecture. Alright, so problem, show that the function is discontinuous at 0, 0. So function has a value on this line. So we have xy line. So here is x-axis and y-axis. This is x equals to y equals to x line. And on this line, value of function is 0. But on the other lines, we have a special formula to show that it's discontinuous at 0, 0. Let's first think about the path approach to 0, 0. If it approaches along the y equals to x line, it always becomes 0, so it exists. However, if I take C1t as t comma t, not t comma t, sorry, so t comma 2t, for example, or in general, if I take the t comma kt, then if I composite C1t, this is nothing but, so this is when k is not equals to 1. So k times t squared and 1 minus k absolute value times absolute value of t, right? So when t goes to 0, what happens? We have degree 2 polynomial and degree 1 polynomial. The sign doesn't matter because t goes to 0, it always goes to 0. So if I take the straight line path approaches to 0, 0, it always goes to 0. But is it sufficient to show that this f is continuous? No, because we may have another path, not straight line, but it's like a curly path. So for example, you can check your path t square. So this is path along this y equals to x squared line, like these lines, y equals to x squared line. So if you approach to 0, 0 along this curved line, then you might have a different limit. So you can check how it goes and see why it is discontinuous. So if you already get the different value than 0, then it's done. But if you get 0 again, you have to find another path. So let me do a few of these problems and then finish our lecture. So the rest of the problems we'll do on the next week. So first of all, let's give a counterexample which implies 2 equals 2 to 1. So the 1 to 4 says the following. So let's look at 2. The function f is differentiable at x0, y0. And the first one says that partial derivatives are continuous at x0. Oh, that's a hard one. Let's do the easy one first. Okay, so let me do the easy one. We don't have time. First of all, let's say counterexample which for 4 implies 2. So 4 says f is continuous at x0, y0, but 2 says f is differentiable at x0 equals x0, y0. So continuity does not imply the differentiability. I want the counterexample of this implication. So I'm saying that this implication is wrong. Okay, so I'm just going to give you a counterexample. So what will be the good example? Let's see. I want to define my f of xy to be let's say absolute value x and 0. Okay, so this is the easiest one. So xy plane, on xy plane, the function is, well, sorry, what am I doing? Just the value of x. Okay, so it doesn't matter about the value of y, it only matters on the value of x. And if I put the value of z-axis, then this looks like this kind of pointy surface. So there is a sharp edge on this surface. So graph of the function looks like this. So if you have such function, you cannot define your linear approximation because you don't have a partial derivative. So fx at 0, 0 doesn't exist. Okay, so lxy doesn't exist. So you cannot even start the definition of differentiability.